Hi, everyone, and welcome to our fourth session on generative AI. We've gathered today together with our colleagues Vlad and Christian to get more in-depth details about generative AI and some advanced use cases. So I will hand over to Vlad and Christian for today's presentation.
Okay, hello again, everyone. I will share my screen in a second. Yes. Okay. Okay, just a second. Oh, so this place. Okay, can you see the presentation and my pointer?
Yeah.
Okay. Let's get right to it. This is our last presentation regarding generative AI. We will cover the prompt engineering because we didn't have time to discuss it on our last presentation. And also we will cover some more advanced use cases with some very in-depth code demos. Okay, let's get right to it. Prompt engineering, I think you've heard about it since LLMs became popular. Basically, refers to methods on how to properly communicate with LLMs in order to obtain better results. The quality of the prompts are directly correlated with the quality of the results. Good prompts minimize biases, reduce confusion, helps the model learn from more diverse data because models also learn from our prompts through reinforcement learning. And overall helps the model to produce more accurate responses. This process helps in saving effort and costs on the long term because having good prompts from the start helps us reduce some unwanted labor down the road. One of the most basic prompting methods is called zero-shot prompting, and it involves asking the LLM for a direct task without providing any context or examples. Today's LLMs are very capable at zero-shot tasks, but as you can imagine, giving more details in your prompt will improve the quality of the output. And this is why we have one-shot prompting, which involves giving one example to a single example in order to illustrate our desired response, either regarding the format or the style or the overall approach of the LLM. For example, we have here to summarize French into English using a specific API template. And few-shot prompting is very useful when we don't have enough training data or the LLM is not trained enough. And of course, as the name suggests, it involves giving a few examples, several examples, in order to guide the performance of the LLM. Chain of thought is a technique used in prompting where we give step-by-step. We want to receive a step-by-step result. So in order to obtain this, we use a step-by-step approach in our prompts. So we ask for specific steps in order to receive specific answers. This is very effective in more complex problem-solving tasks like mathematics, logical reasoning, and multi-step questions. It is a bit better than few-shot learning. For example, we have here a task where we ask the LLM to compute an addition, and since we want to receive a step-by-step response, we give a step-by-step approach. So we ask it to first add 10 and 20, and then add 3 and 4, and then give the final answer. Self-consistence is one step above chain of thought, and it involves the idea of providing multiple diverse reasoning paths. So not just one path, step-by-step path, but generate multiple examples of such approaches in order to receive multiple answers and have a more imperative approach and choose from the best results. So, or doing some kind of averaging. So this is a bit of more scientific approach, just like how we would do like a science experiment. We repeat it several times and get multiple results, and then do an average, eliminate the outliers, and things like that. So this is an example where we, with self-consistency, we have a single path for solving this math problem, and without self-consistency, and with self-consistency, we provide several methods. Of course, this is a specific task which does not really require these techniques, but I used it as an example because in order to illustrate how to structure the prompt and what are the differences between these approaches. Some common tactics for prompt engineering include giving specific instruction in order to leave no room for misinterpretation and reduce hallucinations. Use comparisons or analogies, and sometimes LLMs benefit from repeating the instructions. So maybe when you have a very long prompt and you have an instruction at the beginning, it might help to repeat the instruction again towards the end. Now that we're talking about the end and the beginning, it's important to know that the order of information in a long prompt influences the results. So placing instructions at the beginning of a prompt can yield different results than placing the instruction at the end. Because it might affect the bias in the internal structure of the LLM, and also sometimes it is good to provide a fallback solution for the model. So in order to have like a reserve or something to fall back on when the model fails to respond to our questions. Like I said, prompt engineering and effective prompt engineering helps us in the long run because we have continued use. We don't have to revise our prompts. We exploit the AI to the fullest capacity as much as possible, and we reduce labor down the road and costs, of course. And some of the benefits, like I said, enhancing the quality, we also reduce hallucinations, so we control the behavior of the AI. We facilitate automation where we have LLMs responsible for doing automation, like analyzing data or writing summaries. We improve the efficiency and also reduce the cost because, like I said, every request to an LLM costs money. It is built by tokens, and each word more or less corresponds to one token. and improve also creativity and innovation when that is needed. Okay, let's dive into one of the most used use cases. I don't know if you've heard about it. It's called retrieval-augmented generation, or RAG, and it is a technique for enhancing the accuracy and the reliability of an LLM by improving its knowledge base with some external knowledge. So let's imagine this analogy. We have a courtroom, and the judges need to decide cases based on their knowledge and wisdom and everything they know about the law. But sometimes there are cases where special expertise, niche expertise is required. So judges ask court clerks to go to a law library and look for precedent cases, more specific cases that they can cite and they can use in order to give a better judgment. So we can compare the judge to the LLMs. Like, the judge has a vast knowledge and wisdom of the law. LLMs are able to respond to a wide variety of human queries. But in order to deliver reliable answers on specific use cases and also cite sources, the model needs an assistant. And this assistant, like the court clerk for the judges, is the process of doing retrieval-augmented generation. Now, we have a sequence diagram of how this process works. So first, we have our knowledge base in any shape or form. It can be a database, it can be some documents, some PDF documents. We need to retrieve these documents and first embed them in a vector store or vector DB, what it's called here. I will talk more about vector stores in a moment. Like we discussed in our previous presentations, we use, again, embedding models. So models that embed natural language into machine language in the form of vectors of floating point numbers. Approaches of embedding documents are different. One of the most common ones is splitting the knowledge into, let's say, equal-sized chunks. Each of these chunks will then be represented by a vector, by an embedding vector. And these embedding vectors for RAG have they are very large, like sometimes thousands of elements. So we embed every chunk and we store them in a vector store. After we have the vector store complete, we have the app or the LLM that takes the user query. It also embeds it in a vector embedding vector format, and then the query and the embedded query is sent to the vector store, where the vector store will do a similarity search between the embedded version of the query and the embedded chunks of the knowledge that we have in the vector store. It will return some candidates based on the similarity search. And if you know a bit about machine learning, the first thing that comes to mind when mentioning similarity search is KNN, or K nearest neighbors, where we have some data and we aggregate the data based on its neighbors and the similarity between them. So it's something similar. Like I said, we take the original query and the embedded version, and based on the embedded version, we do a similarity search in the vector on the embedded chunks of the knowledge. It will return a number of similar candidates, which will be sent together with the query, the original query, and the candidates in natural language format as context to the LLM. So I will ask the LLM, please answer this question, then the question from the original prompt based on the provided context, which will consist of the candidates retrieved by the vector store, by the similarity search in the vector store, and then return the response back to the user. Okay, these are the steps that I just discussed. An optional step that may improve the quality of the result is to apply a re-ranking filter on the candidates returned by the vector store. So let's say that we have 10 candidates. The re-ranker filter will, of course, the candidates are already ordered by similarity to the embedded version of the original query, but the re-ranking filter is an extra step to further filter the candidates. So maybe reduce some of the more unsimilar candidates, or maybe reorder them again before sending them as a context to the LLM. Now, like I said, we use vector stores or vector databases for storing and retrieving this knowledge in the form of high-dimensional vector embeddings. Now, what are the key requirements of a good vector store? Of course, support for indexing dense vectors, so native support for that. High-performance similarity search, maybe provide options for choosing the algorithm that you want to use for similarity search, because there are several complex algorithms for that. They need to have support for large-scale data sets, because if you have a large data knowledge base, then there will be a lot of vectors. It should also include, for enterprise applications, of course, support for cloud and infrastructure in order to distribute the computing in clusters and do load balancing and caching and things like that. Also include seamless API and SDK support for any API or language that we want to use. And also, of course, like any database, we want low latency and high throughput. These are some examples of popular vector stores. In our practical demo, we will use Chroma. If you work on SAP Hybrids, you might use Solar, which is embedded into hybrid systems, and many more available vector stores today. Okay, let's switch over to the demo. Just like until now, we will have Jupyter Notebook in Google Colab. I will send you the link to the notebook after the presentation. You will find it on my repo, and you can play with it by yourself by copying it to your drive. And also don't forget to also copy additional files needed for this. So if I go on my GitHub, I think they should already be here. So for example, there are some additional files that you also need to copy to your Drive account, and you will need at some point to give path to these files in order for the notebook to work. Okay, so like I said, we will use Chroma. It is an open source vector database. It is very light for small projects if you want, but also has support, and they are working on support for enterprise uses. It provides a Python native interface and some other extra features like filtering, hybrid search, and so on. Okay, so when you will run this notebook, you will need to install some extra packages that are not included in a Google Colab in a Google Colab machine runtime. So you run this at the beginning. You also mount to your Google Drive and import what we use. Okay, let's create a Chroma vector store. Here, like I showed you before, I hide the paths using secrets. So you will in your own notebook give own paths to your Google Drive locations where you want to work. So we just call the ChromaDB persist client. We give the path. If there already exists this database, we will delete it. The collection will delete it and create it again. This is just for so we can run the code over and over again without having problems. I forgot to mention that in this use case, I will use 3 quite large documents with containing information about electric vehicles. I showed you the documents here. And like I said, you will need to copy them to your Drive account and give the path to them. So we first create a collection that we will call electric vehicles. This is a name that has to be unique in your collections. You can have multiple collections in your for each vector store that you want to use for each knowledge. Okay, we will use a package called PDF Reader. No need to get a lot into in-depth on this package, but we will split the documents by pages, and each page from the PDF document will be embedded in a vector, which will then be stored in a vector store. So we will do just that. We extract the text from each page, and then we add them to the collection. The documents, each document or vector consists of the text that we want to add as metadata, which will then be used in which we can use it to filter documents further down the line and also to identify them. We will use the file name and the number of the page. And we will also need to generate unique IDs for each vector. We will use a separate package for that called UUID. It generates a random ID every time it is called. Now, when we add these documents to the vector store, they are embedded automatically. So we don't need to do any embedding. Chroma offers an embedding model that is used under the hood in order to store the documents or the vectors. Okay, then this code will be a bit more familiar. We create a client, an OpenAI client with our OpenAI API key. Let's define the question. So I want to ask the LLM what types of charging stations exist for charging EVs. I will specify the number of candidates that I want the vector store to return. And we will query the collection with the given question, which is also embedded automatically. We want to include the documents themselves, so the vectors, and also the metadata that we defined here, the file and the page number, the file name and the page number. And we want to have this number of candidates. In our example 5 here, we create an empty string for the context, and then we will parse the results that the query gave. So we will have 5 results in our case. The document will be in the document object and the metadata as well. We parse the context nicely like this. We have the document title, the document page, and the context itself. And then we concatenate all of these candidates in our context string. And then we give the prompt here. I ask it to answer the following question and give reference, document and page. This is why you use that metadata. I also say that if it cannot answer the question, then say, I don't know. So I want to reduce any any case of hallucination. So give specific instructions in your prompts in order to have specific results. And this is the result that it gave. The types of charging stations, and here at the end it also mentioned the document and the pages from which it requested the data. So it also gives citations, but you need to ask it specifically for that. Okay, so this is retrieval augmented generation, a very simple example of doing retrieval augmented generation by ourselves. But OpenAI also includes solutions to that. So we don't need to use any external vector store if we don't want to do. And this is what we will cover in the next. We will cover this in the next chapter. I will skip over the small language models because I want to do them after this. Okay. So OpenAI released, I think quite recently, a new API called the Responses API. So up until now, the basic and the industry standard API that we had until today was called chat completions. It is today very widely used in any apps integrating OpenAI solutions, but OpenAI released a new responses API that the main difference from the chat completion is that it is stateful and it is event-driven. So if you remember in our last demos, in order to preserve chat history, for example, we had to concatenate all of the responses before our current query. So my questions and the LLM's answer, we had to concatenate them all in our context window in order to preserve chat history. Well, now the responses API is stateful and it preserves the chat history for us, but also at the same time keeping the flexibility of managing the order of the responses in the chat. I will show you in our practical demo. And it also includes support for built-in tools such as web search, file search using retrieval augmented generation, function call. There is also a use case called computer use, but I will not demo this today because I don't think it's safe to give computer access to an LLM. And also code interpreter, which is not yet available from OpenAI, but should be available soon. Okay, let's switch over to the demo and then we'll talk about reasoning models because they are also included in this demo. So another Google Colab notebook. This is a longer one. Okay. So like I said, it is stateful and event-driven, this new responses API. If you have problems with using this API in your code, you might need to upgrade the OpenAI package and restart the runtime. I already did that, so I will not run this cell. Okay, let's create an OpenAI client and let's get right into it. This is how the code looks for generating, for simple text generation. We have a model and an input. And if we want, in order to take the response of the model, we use the output text field of the response. And one thing to notice here, that each response from the model generates a unique ID. So if I generate this, if I run this cell one more time, we will see that we will have a different ID each time and a different answer as well. Okay, this is how the response object looks like for simple text generation. We have the ID here. We also have the time of the creation. We have the output here. And the annotation list It's something that I will discuss a bit later. And also some other details about the input and the output token. So if you want, it is easier now to keep track of your token usage by accessing these fields in the response object. Okay, let's see how do we preserve chat history in our messages with responses API. So we will make use of the unique ID of each response, and then this very nice field here called previous response ID. So I think it's very suggestive that if we have a chain of 2 responses from the AI. So for example, we have the response here for a query that asks the AI to tell a joke. And then we will have a second response in which we will provide the ID of the previous response as the previous response ID and ask it to explain why the joke is funny, okay? So we will have here 2 separate answers. Okay, let's generate it again. And here is the joke, here is the explanation. So I didn't need to include the joke again as a context. I just used the ID of the previous response of the responses. So these responses are stored by OpenAI by default. This is the stateful part. And this enables us to use only the ID of responses in order to chain the messages in a chat history. If we don't want the responses to be stored by OpenAI, we can set the store parameter to false whenever we call the responses create method. Okay. Just like the previous API, we are able to include instructions in our queries. So for example, in the instructions field here, I will tell it that it should act like the LLM should act like a helpful assistant called Lisa. And I tell it here that my name is Vlad. What is your name? Hello, Vlad. I'm Lisa. How can I assist you today? These instructions, these instructions come at the very beginning of the prompt, and they are used to define the behavior of the LLM and how we want our responses to look like. There are multiple roles for giving instructions here. Like you see here, we can use roles in our messages. But the simplest way is to just give them in the instructions field here. Now, how do we string the responses? I showed you last time that you can have a nicer UI experience by streaming the responses. It looks something like this, just like you would use the interface on the ChatGPT OpenAI site. When you don't have the whole answer return, you just have them word by word. You can do that in the responses API, but this time it is a bit different. So like I said, it is event driven. So there is the responses from the LLM are events, and we have different type of events. One of the most common events for streaming text are in this order. We have the response created event. Then when we use streaming, we have response output text delta. So each word is contained within one of these events. We have the completed, and we have an error. Then will also be an event error. So if I ask it here that my name is Vlad, what is your name? And we output each event. And in the case of delta events, we also output the text. We see that each event contains a token here. And we also have the created, in progress, and some other events. You can play around with these events in order to improve your experience. So during the in progress events or the created events, you can show, I don't know, a UI element stating that the generation of the response has started. Then you stream your deltas here, and then it is done. So like before, like I mentioned, we only are interested in this simplest case on the event type output text delta. So if it is such an event type, then we print the event data, the text itself, and we use flash equals true for the print function to work properly, to not buffer the output and then have like a lag in our output streaming. Okay, image input, very straightforward. You can give some input text and ask it like what is in this image, and then you give the image URL. Here it is the URL of an image on Wikipedia that is shown here of type input image. You print the output, and then you have the description, which is quite detailed. Now let's go into the more advanced stuff, the built-in tools. They are external tools, separate tools that LLM calls separately in order to extend or improve its capabilities. And let's start with function calling. You can use function calling in order to give the model access to your own custom code that you might want to call in different situations. Now, one thing to note about these tools is that the model decides by itself when there is a need to call any of these type of tools. Of course, you can use some parameters in order to force using these tools, or maybe disable them entirely, or maybe specify which of the tools you want to use. We will see that in further examples. Let's get back to function calling. What are the steps? So first, of course, you need to define your custom function that you want to call. And then when you call the LLM, you describe this function by using a special schema that includes what the function does, when to use the function, and what input arguments it expects. So the LLM will not see the code or the function itself. It will only see a description or a schema of the function, and then it will generate a response that will contain the function name and the given arguments. And then you have to call the function yourself, provide the response, provide the output of the function as a response to the LLM, and then it will incorporate that response and the output of the function in a final result. So let's see a use case where we want to ask the LLM to give us weather information for a given location. So here we have a simple function that does a request to an API of OpenMeteo, in which we include latitude and longitude coordinates for a location. And it returns the temperature in Celsius. So we have this function here. And then in a tools, in a list that will be added as a tools in the tools parameter. So this tools list will contain the description of what built-in tools you want your model to call when you generate the response. We say that we have a function with the name getWeather from here. We give a short description in natural language in order for the model to understand what this function does and when it should call it. And then we provide the JSON schema defining the function input arguments. So we have, in our case, we have two properties of type number, latitude and longitude, which are required by the function. So we have the input message, what is the weather like in Paris today? Notice that we do not give the coordinates ourselves, but we leave the LLM to determine that based on our question and based on this description here. So it is able to produce here a function call with the required coordinates for Paris. without mentioning them explicitly. So here we have the arguments object with latitude and longitude of the city of Paris. We have oh, okay, just a moment. I have a problem with my monitor. Just a second. Okay, sorry for that. Can you still see my screen, the share screen?
Yes.
Okay, thank you. Sorry for that. So, like I said, we don't give the specific coordinates. We let the LLM determine that by itself and generate the call for the function by itself. This is one of the best way to explain how the LLM makes use of this function calling feature. So we have like I said, the arguments here, the latitude and longitude determined for the city of Paris, and the name of the function, of course, type, this response is of type function call. We parse the response, so we take we will create a function call here with this parameter. So we get the function name here, get weather, and then we parse this arguments object in order to get the input arguments of the function call. In Python, it is important to know that you can have specific input arguments here, the name and the value itself, separated by comma. Having them like this enables us to have the input parameters in any order. So if the LLM somehow reorders the parameters, if we mention them specifically, explicitly like this, then the order doesn't count. And we also can have a comma after the last input parameter. So this is the generated function call based on these values here. We call this function using the eval method in Python. So we take this string here and then add it as a parameter in the eval function. And here is the current temperature in Celsius in Paris. Then in our input messages, we add our we add our original question. We add the tool call here, so the whole response here, this whole response, we added as well to the input messages, and we also append the result, the output of the method as type function call with the call ID that we take from this function, this call ID parameter, and then the output is the result that we computed here in string format. And when we want to generate the response again, we have a nice answer for the LLM with the current temperature in Paris today is 13 degrees. Now, like I said, if you want to add some additional configuration regarding telling the LLM how you want these tools to be called, you can leave them in auto. You can specify that it needs to call at least one of these tools. Then you can be even more specific and provide the list of tools that you want it to call. And you can also ask it to not call any type of tools whatsoever. It's important to know and always keep in mind when building applications with LLMs, keep in mind token usage because they cost money. They don't cost a lot, but if you have a large, if you have a very high throughput of prompts, then the cost will add over time. And keep in mind that these functions are injected into the message, into the syntax, the context window, in some kind of system syntax that the model has been trained on. So they will count as tokens. Okay, so functions will add to the cost of calling LLMs. If you run into token limits, context window size limit, you might need to limit the number of functions because you can give multiple functions for the LLM to call, not just one. And also limit the length of the description, maybe work a bit on the function schema, reduce some of the parameters. Maybe you can reduce some number of parameters and things like that. Okay, our next built-in tool, which is also available on the OpenAI interface, ChatGPT interface, you might have noticed it, is called web search. It allows the model to search the web for the latest information. You might know that LLMs have knowledge cutoff at a specific date, which is in the past, of course. If you want the model to give some latest information, actual information, you need to use the web search built-in tool. Like any other tool, like I said, the model decides or can decide if it uses this tool or not. So in our tools list, we specify that we want to use the web search preview, and we ask it what is the positive news story from today. This is from yesterday. I think today we'll have some different stories. Let's see. Okay, so we have some different stories here. Notice that the model, when it uses the web search preview, it also gives citations, inline citations, but they are, simple ones, URLs to the articles that it mentions. If you want to have more control over the citations and maybe display them somewhere, be a bit more specific about the page when you use, maybe you use a scientific article. The citations are found in the annotation list. If you remember the big response here, the citations will be added here in the annotation list, and you can access them in the response object. And here I printed them as JSON. So yeah, the file ID not relevant right now, but we have okay, sorry, web search. We have okay, this okay, I needed to generate it again. Here are the citations that it used. So these citations here, it also give them, it also are cited here with the start and end index and the title and the type and the URL. Okay. If you want to give a bit more, if you want to have to search the web given a user location, you can include it here in the user location field, the country, the city, and the region. You have to use specific formats. So the city and the region are free text strings. The country needs to be an ISO code, and if you give the time zone, it also needs to respect this format here, the IANA. Okay, so I ask it here, what is the weather like today, without mentioning the location in the prompt, but I give the user location here in the user location field. So a similar use case for the one in which we used function call, but here we use it for the same use case. We use the web search capability, and I give my location in Iași, Romania, and then it will output detailed weather information for Iași, together with a citation, of course, and the forecast for the following days. Now, let's talk about token usage again, because you need to keep that in mind. The tokens used by the search tool do not affect the context window. So you don't need to worry about running into limits when using web search. But web search also are counted and built as tokens, even though they are not included in the context window. So you don't have problems with the size. You will have problems with costs, of course. And you can give values for how much context you want in your web search, from high to low, in order to keep control of your billing, of your token billing. Okay, now let's go to our latest built-in tool, which is similar to what we did in our previous retrieval augmented generation demo, but we use OpenAI's vector store. And of course, just like the other tools, the models decide automatically when to use them. And it will call and retrieve the information whenever needed. So what are the steps? You upload the files to OpenAI, you create a vector store, add the files to the vector store. You need to wait a bit for the embedding to be done because it is done under the hood. And then when you query the model, you include the vector store ID as a parameter in the tools list. Okay, so we will have the same use case with the free documents with information regarding EVs. We don't need to do splitting anymore because OpenAI does that automatically. But first, we need to open the files and upload them using the client files create method. This is the client from OpenAI, remember. We need to specify here the purpose is for assistance. The assistance, just small mention, the assistance and the assistance API is a separate API for creating a custom OpenAI assistance, but it will become deprecated in the next year, and it will be replaced by this responses API that I'm showing you here. So you upload the files to OpenAI, and then after uploading them, you can see them here in your OpenAI platform page, in the dashboard tab and in the storage tab here. And here are the documents that I uploaded yesterday when I worked on this notebook. I will delete them and upload them again just for you to see them here. Let's run this cell again. Now, these file IDs, I will also store them in a list that I will use when I will add the files to the vector store. So if we refresh this page here, we see the documents appeared here, uploaded right now. Okay, we create a vector store. We will call it EV documentation. And after you create it, you can see it here. I deleted the files in this vector store, so I need to create it again. So let's create the vector store again. And let's also add the files to the vector store because this will take a few minutes. I mean, 1 or 2 minutes. The files are not that big. If we refresh this page here and go into this vector store, we can see that they are attached and uploaded, and I think they are ready to be, they are already embedded, so ready to be used. Of course, like I said, you include it in the tools list as a type file search. You include the vector store that is returned here. When you create the vector store, you include it here in this list. Now, one thing to remember is that I forgot to mention here, but I will write and then update it on the GitHub, is for now, you can only use one vector store for querying. For now, in this responses API version. In future, you will have support for using multiple vector stores. And the output is like we expected. It's a bit slower querying the vector store, but it works. And let's not forget, if you want to have citations, we have them here in the annotation field. I use the print annotation method that I defined above, and here are how annotations look. Here it gave me how many candidates? 1, 2, 3, 4, 5, 6, 7, 8 candidates. This might be the default number of candidates. You can limit the number of candidates, and you can also include the search results in the response. So here in the results field of the response object, you have here the candidates themselves. So these are the citations. I forgot to mention the name of the document and the index. And these are the results themselves if we have them here in the includes list. These are the text snippets that are used as the candidates of text snippets that are used as context for the LLM to provide response. We can also see here the file name from which they come from, and we also have the score, the similarity score, and we can see that they are ordered from high to low. So the first candidates being the most similar ones, and like I said, we can limit the number of results here in the tools in the maximum results parameter in this tools list, and here we have only two results, and therefore only 2 citations, and so on and so forth. Okay, we will talk about reasoning models. I think you noticed that when you use ChatGPT in the interface on OpenAI, you can also enable reasoning together or not with web search. Now, reasoning models are something new from OpenAI. I think we discussed about one reasoning model before from DeepSeek called DeepSeek R1. This is Google OpenAI's response to that. Reasoning models. So they are new language models trained with reinforcement learning in order to perform complex reasoning. They do think before they answer. So if you use the ChatGPT's reasoning in the interface, you will notice that before giving the response, it will take a bit and it will show you, oh, thinking about this, reasoning on this. Okay. They are good for complex problem solving, coding, scientific reasoning, and in general, multi-step responses. These are the current available models for reasoning. We have, they are ordered by power. O1 Pro, it is the best one, the most expensive one. Like you can see here, it is very expensive. And it is only available through the Responses API only. Responses API only. Then we have the O1. They all have the same context window, by the way, and the O1 models also support images as input, which is something in between, and what we will use for simple demos. And they are very capable as well. These mini models, like I told you before, the O3 mini only takes input as text, and it is much more cheaper. So reasoning models introduce new reasoning tokens in addition to input and output tokens. These reasoning tokens, they are discarded from one, if we have a multi-step conversation or a multi-step answer, these reasoning tokens are discarded, as you can see here, as the context window increases, and we will at some point reach a context window limit. You can see here that the reasoning tokens are not included in the next phase of the conversation, but they are billed as output tokens. So keep that in mind. Now, how to choose between models when you need speed, cost efficiency, and when you have well-defined simpler tasks like summary or I don't know, something specific, GPT models are better. But when you have something more complex, something that needs that the model a task which is a bit ambiguous and the model can handle it and it's very complex and multi-step. So for more complicated task, you can use the O series models or the reasoning models. Now, some of the use cases, navigating ambiguous tasks when you have limited information, when you have limited information, the model might be capable, in most of the cases is capable of understanding the user's intent. If not, it will ask clarifying questions, which is very nice. If you don't give the prompt enough, then it will ask for some additional questions in order to have a better understanding. When you have large amounts of unstructured information, and reasoning models are able to handle a large amount of unstructured information and also find relationships and nuance across a large data set. So if you have some relations, semantic relations in a big document, reasoning models are generally capable of understanding those nuances. Like I said, for multi-step planning, this planning is an interesting use case that I saw on the internet, where you use multiple LLMs and you have the reasoning model as the planner, and then assign specific tasks to GPT models. So if you remember the DeepSeek architecture, where it uses I think it's called I think a group of experts or something like this. I forgot the name. Where it is something like an application built on microservices, where you have a gateway and then it will forward the request to each service individually. It had an expert network that is a gateway network that will call each expert network for a specific task. This is like something like that, but one step above. We have the reasoning model, the planner, which will choose which GPT model to use and then forward the information to that. So you can combine them for very complex tasks. The visual reasoning is better than GPT at describing images, understanding structures or unclear images or ambiguous objects in the images. And it is better for reviewing, debugging, and improving code quality. Now, because these reasoning models have a higher latency, these are good for tasks, like I said, for reviewing and debugging, or maybe writing documentation. But for code generation, you might want to use GPT because that is faster, better, and a bit more specific. Now, how do we prompt these reasoning models? If we use classic prompt engineering techniques that I mentioned before, for example, instructing the model to think step by step, we might hinder the performance because the model already will provide a step-by-step explanation. If we limit the specific steps or the format of the output, we might miss some things that the LLM might be able to do. So you can give instructions as developer messages, just like the instructions that I showed you in the responses API. You can give them with a developer role, and these are used for the reasoning models, and the system instructions are used for the GPT models. You have to have simple and direct prompts because they are good at understanding to clear instructions, you don't need to give a lot of specific. Of course, it is good to give specifics, but try not to limit the capability of the LLM. Avoid chain of thought prompts because they already think step by step, and use the limiters for clarity, like XML tags, bullet points, or things like that, in order to delimit the information in the prompt. Try zero shot first, and then few shot if needed. Reasoning models are excellent at zero shot prompting. Provide some specific guidelines. Of course, always be specific in your prompts and about your end goal, what you want to receive. Okay, let's switch back to the demo and show you how we call a reasoning model. We will use the O3 Mini because it is cheaper. I ask it here to write a bash script that takes a matrix represented like such, and then prints the transpose of the matrix using the same format. So I ask it to do something complex that contains multiple steps and multiple instructions. I call the model O3 Mini. When calling a reasoning model, you can specify the effort. So how many reasoning tokens to use, like I mentioned here, you can give low, high, or medium values for this parameter. The medium one is the default one. Of course, high will use more reasoning tokens, which cost more, but it will give better responses, but slower responses as well. And this is the result, a very complicated bash script that it also contains explanations and comments and whatever you need to understand this script, and also the usage example. Okay, so this is the responses API. We have a few more minutes to talk about small language models. If you have any questions about this new responses API, the documentation from OpenAI is very detailed. So if you need further information, I encourage you to consult the documentation. Just be aware that it is a bit sparse. Some information that I think should be included in a single article are split between multiple articles. But if you go to docs, you can find here, for example, information about the built-in tools, and you can switch here between the two available text or not text available APIs. So the previous standard API chat completions that I showed you in our last presentation, and this one, the new responses one. So when you consult the documentation from OpenAI, make sure that you select the API version here, because as you can see, the code changes a bit when you use different types of this API. So if there aren't any questions about the responses API or about reasoning models or whatever the tools we discussed, let's talk a bit about small language models. So small language models are lightweight version of traditional language models. They are designed for efficiency, and they are designed to run on resource-constrained environments, on smartphones, embedded systems, computers. So not like the LLMs, which are run on supercomputers or servers on multiple GPUs, expensive GPUs, are not the consumer grade ones. Now, these parameters range from 1 million to 10 billion parameters, while large language models have hundreds of billions or even trillions. The number of parameters for modern large language models are not disclosed anymore. Of course, that means that they are significantly smaller, but they still retain the core NLP capabilities, like generation, summarization, translation, question answering in general, maybe some code generation. But like I said, they are designed to run on resource-constrained environments. Since they are significantly smaller, they are significantly faster compared to large models. And since they are smaller and easier to run, they are easier to fine-tune for specific tasks. Now, these SLMs are created through the process of shrinking large language models. Some techniques include knowledge distillation. So you train a smaller student model using knowledge from a larger teacher model. So you don't use the raw data that was used on the large model. You use data outputted by the large model in order to train the student model. Knowledge distillation is something that DeepSeek used to train its more efficient expert networks. And if you, I don't know if you read in the press that there were some controversy because it was accused of using OpenAI models as teacher models and use distillation from OpenAI in order to teach their own models, which I think is something very smart that what they did, and I don't think it's illegal. I don't think, since this data is available for everyone. Now, some small language models are also created through pruning. That means removing less important parameters within the neural network, and also by reducing the precision of numerical values in calculation. Now, some of the trade-offs are narrow scope. Of course, they are smaller, so they can't really be generally good at everything like large language models. So you have to have them for limited domains. They need to be expert in the domains that you want to use it. So a medical SLM will struggle with coding, of course. Being a smaller network, you will encounter bias risks, because if it was not trained correctly, it might have a bias towards something. Of course, they are smaller models, reduce complexity, so they will struggle with nuanced or complex tasks like reasoning tasks. So these are at the very opposite end of reasoning models. And of course, they are more prone to errors like hallucinations and stuff like this. What are the applications of SLMs? You can have them as chatbots, virtual assistants. For example, I think for the latest version of iOS and iPhone 15 Pro, 15 and 16, the Siri was improved with an SLM that runs on device, because there were a lot of concerns about privacy, because you can also, when Siri is not able to answer a question, it will ask a GPT. It will call an OpenAI API, a GPT API, to ask to solve more complex tasks. But the Siri now, it's an SLM that runs on device. You can have them as code generation for a specific language, or for a specific task, or for a specific project. You can configure an SLM for just a project, bigger enterprise project, and give the code base as training, and then assist you in your coding tasks. Language translation, summarization, healthcare application, and IoT, because they can be implemented on embedded devices. Now, for a demo, we can use Ollama, an open source tool for managing and integrating SLMs on PCs. It is available on Linux, Therefore, it is also available on Mac OS, and now I think it is also available on Windows. You need to install Ollama from this URL, and after that, command CLI is installed, and you can open a terminal and run instructions. Now, let's see what available models we have on Ollama site. The models are here. You can see there is a range tool of SLMs for different tasks. You can run embedding locally. You can do vision applications. Let's look at the Gemma 3, which is a lightweight model, an SLM from Google, built on Google Gemini technology. You can download specific variants of this SLM, this being the number of parameters. So this one has 1 billion parameters, around 800 megabytes in size. And as the parameter increase, also the model size increase. And you have information here about the context window and evaluation and some certification of evaluation. Okay, let's see how it looks. So this model is from Google, a smaller version of Google Gemini. We can use the Ollama ls or list function to see our current installed SLMs. Here I have Gemma 3 1 billion. Let's remove it and install it to see how it looks. Ollama Gemma 3 1 billion. If we run Ollama ls again, can you see the text clearly? I made it a bit bigger. I hope it's all right. If we run Ollama ls again, we see that we do not have the Gemma 3 anymore. How do we get a new model? We look here. We can run it directly, and if we don't have it installed locally, it will download it and then run it. Now, I think it is better to pull it first. So we will use the Ollama pull function, and we want Gemma 3 1 billion parameters because it is smaller. And you have a nice interface for showing the progress of the download. It shouldn't take more than 1 minute, I think, for this smaller network. Okay, now we run Ollama ls again. ls, and we can see we have Gemma 3 available, modified 6 seconds ago. Let's run it. Ollama run Gemma 3 1 billion. And now we have an interface for querying the network. So I would say, hello, my name is Vlad. How can I help you today? What is my name? Okay, so we do not have in this interface implemented chat history. That's not a problem. So you can ask whatever you want here, and it is run completely locally. I tested it, I disabled Wi-Fi, and it ran perfectly. When you want to quit the chat, you type /by, but please remember that the model is running, it is still loaded into memory. It will still run in the background. If we run the Ollama PS function here, we will see that it is still running. It is using 100% of my GPU. So please remember to stop it. I think it will run for 5 minutes and then it will automatically stop, but just stop it when you're done with it. And when you run Ollama PS again, you can see it is not running anymore. Now, you can copy every model here and create your own version of it. Okay, so here are some instructions that I already showed you. Now, let's copy our model I think I have here. Let's customize our model here. So let's create a, okay. I want to create a custom model, a custom assistant. We do that by copying an existing model like Gemma, and we will provide a model file with some instructions for our custom model. For example, here, I use the model Ollama 3 from Facebook. You can use whatever model you want here. Now we will use Gemma. You can set the temperature, for example. If you remember, temperature is from 0 to 1 being the most creative, 0 being the most thorough, the most specific. And you can set a system message. So I call it here, you are Mario from Super Mario Bros. Answer as Mario, the assistant only. These are the instructions to run. So you give a path to your model file. After you copy your model using this instruction here. Oh no, you don't need to copy it using that instruction. When you use model file, you use the create with the model file path. You give a name here, and then you run it. Let's try, let's see if I can have a model file here quickly. Okay, so for model file, what do I have here? Okay, I use the Gemma network. I set the temperature to 1, and like in the presentation, I ask it to respond as Mario from Super Mario Bros. So we have this model file here. We are in this directory. So let's call Ollama, create Mario, and the path to the model file. We don't have this model. No. If you look here, we do not have this model created yet. It created it very fastly. So when you call Ollama ls, you can see that we have Mario here. And now if you run Ollama Mario, excuse me, run Mario, hello. You can see that it uses these emojis from the Mario game. What is your name? My name is Mario, nice to meet you. You can call me Mario. Okay. So this is how we create custom models. Let's see how we can input as images. I think I also have something here. Oh, of course. Ollama also offers a REST API. So if you want to create an application that uses an LLM locally, you can start the server with Ollama serve and then call the API, the REST API methods in order to obtain responses from the model run locally, or maybe you can deploy it somewhere on a server. Of course, this is how you preserve chat history by appending the messages, the sequence of messages. I think I also have an example here on how to use. Let me see. API generate. Okay, so Ollama is already running. I have the example here. I call it using this path here because this is the default path for generating responses, the API. I ask the model Gemma 3.1b, why is the sky blue? When I run this, I think Gemma will automatically load the model into memory, and then it will give us the response with some fields here. I think, okay, this is the response. The sky is blue because blah, blah, blah. Yeah, and I think I also had an example, but I forgot about it, about vision tasks. Let's see. This is lava. You can use it with vision. Okay, so this is how a prompt looks like. What's in this image, and then you give the image path. So let's take the image path from this puppy image here. that in a moment. Okay, copy as path name. Let's see what model it is running now. You can see that the model remained in memory, so please remember to stop it if we have limited resources. Okay, Ollama run Lava. This is the vision, the multimodal, a multimodal SLM. So I call it what is in this image. I'm gonna give the path, my local path, and name copy.png. You can see it added this image, and you can see it shows a description, like in the image here, yellow Labrador puppy sitting in the grass, looking towards something with its mouth open. So you can also input images, and of course, you can call it using the API, using this syntax here. I think this one needs to have the image in bytes format and not as a path for the API. Okay, so I think this might be it for the demo for local for SLMs. Yeah, this is how you run local models locally without calling any API, without sharing any information to any organization. And this was run on a MacBook M1 Pro, I think, or Max. And as you can see, it was pretty fast with any task that we gave it. Of course, I don't think it has integration for these GPUs from Macs. It uses the for Mac or Mac laptops. It uses the CPU, I think. But if you have a desktop with NVIDIA, I think it has integration for that. Right? NVIDIA. No, maybe it's not here. Yeah, and if you look here on the Ollama GitHub, you have more information regarding the CLI and managing models and also the REST API. And here is a list of applications, open source applications that utilize Ollama, integrate them locally for any type of task that uses LLMs. For example, here is a VS Code extension that enables AI helpers. Yeah. Okay. So that would be it from my side. I will stop sharing my screen. Everything that I showed you today will be available on the GitHub repo. I will send you the link again to the repo. If you have any questions, I'm very happy to answer them. Yeah, and just like I said, hit me up anytime you want to discuss anything regarding AI, and I will try to do my best. And so, any questions for today? That means that I was clear enough.
What's more to ask? Come on, it's
Yeah, there are a lot more things that I didn't cover, but they are truly advanced stuff like fine tuning. You need the serious hardware for that, even for SLMs. So I didn't cover fine tuning. Maybe in a future presentation, but I don't expect that my current work hardware to be able for that in a manageable time. Yeah, so fine tuning is still is a lot more costly hardware wise compared to just running a model. Yeah, but I think you can do fine tuning with Ollama. I think if not, there are There are a lot of frameworks for that.
So for now, this is the last part of this series.
This is the last part for now. For this, I would call it an introductory series.
But you guys will continue your research, and if you
course.
find something else interesting,
Never stop learning.
Also, there is something interesting called operators from OpenAI, but it's not available in Europe, just in US. So it's pretty interesting, but we cannot access. Yeah.
When we'll have legislation for that, we'll play around with it and maybe do another presentation.
Or anytime you find something interesting to present to us.
Of course, of course. And anytime you have any type of curiosity regarding the subject, just message me or Christy and let's have a chat, let's have a call and see what we can discover together. So regarding the OpenAI APIs, remember that this API that I showed you today, the responses API, is the intended future for OpenAI, an API from OpenAI. But chat completion still remains the industry standard. So it is still the API that is used widely today. There are some documentation for migration from one API to another. Chat completions, they say that it will be supported indefinitely. So there is no deprecation date for that. But you might expect that the responses API will at some time replace it entirely. Yeah, so if you're starting new with a project using OpenAI, I suggest that you go directly to this new API called responses. This is what OpenAI recommends. Because it is a lot more capable, it is more refined. Like I said, it is stateful, event-driven, a lot more robust. I think they have some speed issues, some latency issues. At the beginning they had that, but I think they will solve. I think it is as fast as chat completions for them. Okay then, so if there are no questions, we will end the presentation here. It was a joy working on it. I also learned a lot from it. And thank you a lot for your attention and for your engagement. I will send you the repo containing the presentations and the demos and all of the required files. If you have any problems running the demos, let me know, send me a message and we'll figure out together. But using Google Colab for learning, it is the best approach. And after that, when you want to do something locally, okay, you can start on installing a Python environment and then setting up environments, installing required packages, and things like that. But using Google Colab to get used to Python and get used to using notebooks I think is the best introductory approach.
Well,
okay.
So thank you, Vlad, and thank you everyone for joining today. As mentioned, this was the final session out of the 4 that we have planned so far on generative AI. And I will share the recording after the call. I hope these sessions helped you getting a deeper understanding on machine learning, generative AI, LLMs, and of course, very practical use cases. So I encourage you to continue experimenting yourselves and use the resources that Christian and Vlad shared and will share also today. And at the same time, if you have suggestions for further related sessions, please approach us and we'll try to plan them as well. Both guys are available on Teams when we're not busy with their projects. So feel free to contact them. And again, many thanks, Vlad and Christian, for making these sessions happen.
Thank you.
Thank you.
Thank you as well.
Thank you.
Wish you everyone
Have
a
a
good
good day, everyone.
afternoon.
Have a good day.
Thank you.
Bye.
Bye-bye.
Have a nice day. Bye bye.
Bye-bye.
Bye. Bye.